All right, today we're going to talk about continuity, and this will be finished of chapter two. Unfortunately, this is pretty long, so we may take it in 2 days, and then we'll start chapter three, chapter four. Chapter three and chapter four will be long ones, but then chapter five only 2 or 3 sections. So
I was reading through on continuity last night. It does look like a pretty long chapter.
yeah, so we won't do too much. We'll get halfway through, and then we'll stop and we'll pick it up next time.
But is this the last section of
Chapter two, right? Because I don't think there's a section six.
Uh, I don't know.
If there is, I won't do it because continuity. That's the one because we always talk about a function has to be continuous.
Right.
How is it continuous? What has to exist? And this is where we're going to define it, the whole process now. All right. Let's forget. I keep on forgetting to turn everything off. Stop talking to me.
Yeah, we get sidetracked.
And you can hear me. You can hear me okay over there, right?
Yeah, but now I can't see the screen on.
Yeah, because it switched over once I turned the camera on. So there's that. You should be able to see it now.
Yeah, I cannot do
Right. If there's anytime I turn the overhead projector on, it kicks me out of Zoom. All right. So let's look at continuity at a point. Because yeah, we can define continuity by saying if you put your pen on the paper and keep on drawing the graph and never have to lift it up, that is continuity. But there's a much more accurate definition of it because every point has to be reachable, has to be defined. And that's what we have to look at here, and we use limits for it. All right. Let's look at an example first. So to understand continuity, it helps consider a function like the one below. At which point does the function f not appear to be not continuous? Now, which numbers above? Yeah. And what occurs at the other numbers of the domain? So what do you notice here? Where is it not continuous? At f of 1, it's not. Why is it not continuous? Because it's a jump discontinuity. And that's what it's called a jump discontinuity, but that's exactly what it does. Okay, where else? What's happening at 2? Has a hole. It's open. It is a removable discontinuity. Why is it called a removable discontinuity? Because if we looked at that function in an equation, let's say we had x squared minus 4 over x minus 2. At 2, it doesn't exist. So, but if we take it away, if we cancel it out, we just remove that discontinuity. Now it comes into a function. So whenever you cancel out, if you have a function that's 0 over 0, you can remove something. That's removable discontinuity. Yes. So get this thing too far up. Where else? And at f of 4. What's happening at 4? Yeah. Thank you. That's such a huge difference. Another removable discontinuity. Because yeah, it's approaching here, but then we're also going to look at, we're going to prove the reason why it's not continuous at that point. Besides it, obvious, the pen thing, you have to move it to the other side.
So there's a difference between a removable discontinuity and a jump.
Yes, because a jump discontinuity, it's the function itself continues at two different. On the left hand side, it's going this way, and right hand side here. On the jump discontinuities, it's from the left hand side, it's approaching this, but then it jumps there, and then comes back again and starts again from here. So it's just that one number has been just removed. But this one, this function and this function. It's kind of like if you have a piecewise defined function. That's what that is. Its function is defined on both sides, but they're not together. This one is just one point that's removed.
And so there's.
Right. Okay, let's look at the next one. Numbers at which the graph of a function has breaks. Okay, first off, what is an interior point? Right. That is inside the open or closed interval that has a limit on both sides. In other words, the limit exists on both sides. So, for example, at an interior point at x equals 1, or x equals 3, it doesn't matter what we pick. If the function fails to have a limit on one side, or both actually, then it is discontinuous. I'm not going to use not continuous. I'm going to use discontinuous. Because what the book a lot of times uses, it's not continuous. This is going to be important thing. If it fails to have a limit on one side, only one side, and the other side doesn't, then it's discontinuous. So the function is discontinuous at x equals 1. Because at this point, at the left side, as you get closer to 1, it may exist, but on the right hand side is so how can what can cause that? What can cause that to happen? Right. Like a stepwise function. The greatest integer function. Greatest integer function.
So with the greatest integer function, if x is like one, or like, let's say x is like 3.2 or something, then that means that, the f of x would be 3, right?
Well, it's always going to round down. So it'll be 0 all the way to 1, and then it jumps to 1. Then up until 2, then it jumps to 2. To -1. It'll continuously do that. I mean, I always say it rounds down or it truncates the decimals. Except when you get to the negatives. If you truncate the decimals, then it would round to 0. It'd round up. So that's why I have to round down. Because think of it this way: if we had 0.1, what would that be? It'd be 0, okay? But that doesn't work there. So we have to go down. What's the next one down? I said -0. It'd be -1, right? So you have to round down, which is what these two. If we had 1.5, it goes to 1. It truncates, but it does more than that. It rounds down. That's the easiest way to define it. Again, now when you try to program, there is a gradation of GI function in computers, but if you try to define it yourself, how would you define what to do? You can't say, okay, truncate. I want 0 decimal places, 0 significant points. You have to say, you have to tell it to round down. If greater than, then go down.
And that's what they do when they program the GI function.
Mhm.
What is the GI function used for? Is it used extensively?
Not really. It's used when you only want integers as your final answer. You can have any input you want because the domain is all real numbers, but your range is simply the integers. So that's what would be an application of that. Well,
Maybe if you had to, you can't, if you're counting the population or something.
yeah, you can't have a 0.4 of a person.
Right.
Yeah,
Or
exactly.
you couldn't even have 0.7 of a person, so you'd have to round down with that.
Round up, yeah, round up, or yeah. So then you look at, do I round up or round down? Because now I deal with people. Because if I round up, I've increased the population by 1. If I round down, I'm not representing all of them. So that's why decimals are very difficult when it comes to that. So you have to pick one and stick with it. But yeah, if it was populations, I would use the opposite. I'd round up.
Oh, you would.
Well, yeah, because think of it, because I'd rather be safe than sorry. Because if you always round down and you budget for fewer people, you don't have enough money. But if you over budget, then you always have a surplus.
That's where this comes in.
Yeah, so that's happened a lot of times.
Better than believe that they're going there.
Exactly. And what your companies do, if you ever work for a company, they'll always say at the budgeting, always use what you had last year and then raise it 25%. Because well, if not, if it doesn't grow, I at least have that money and I'll spend it for something at the end of the year. That's why November, December in corporations, massive buying season because you have to spend whatever you have, use it or lose it. Because if you don't use it, then next year's budget you cannot ask for more money. So you have to make sure you're out of money well before the end of the year. And trust me, when I was in charge of the systems group at DFW, oh, you see these huge orders for we need 40 more coffee pots or like I mean, you name it, they'll order stuff that they want, not what they need,
Yeah.
just because they have to make it a zero balance. So, yeah, we'll show you in pictures when there is a function that has a break. So, hold you one second. Let's take another example here. Numbers at which note breaks. Numbers as which the graph of a function has no breaks. Let's say that when x equals 5, f of x equals 2. What can we say about that?
Well, it tells us a couple things. It tells us that the function is defined at 5.
It's defined at 5, yes. F of x is defined at 5. What else? That the limit exists. What would the limit be?
Would be 2.
Right. So we know there's a limit of f of x as x approaches 5, it equals 2. In order for that to happen, we talked about last section that this thing has to, it has to be able to come from the left and from the right, and we get the same value.
And so we also know that it's continuous at x equals 5.
Because all the numbers, but in section 3, were the ones that we're flubbing along. Remember, what we're looking at here is for any function at some value c, we have a band. We have c minus delta, and at this point we have c plus delta. This distance is delta. As delta goes to 0, these points get closer, closer, closer. What that means, it approaches some function, some value f of c, where this is L minus epsilon. This is L, well, this is plus epsilon. This is L minus epsilon. So epsilon represents these values. As epsilon goes to 0, our limit exists at f of c. So as you can see, on both sides, it has to exist. This is, on this side, we're saying the limit as x approaches c from the left. On this side, the limit as x approaches c from the right. And if it both leads to the same point, then it's continuous, because it has to be, because it's approaching both sides. As opposed to a one-sided function. Remember that one? The half circle? We had endpoints here. It's not, is it continuous? Well, it is continuous on this bound, but it's not continuous over the whole domain. So we have to determine on where it's located, where it's defined on. So that's the part that we have to be very careful about. Yeah, let me put this up there also. Are you ready? You finished? Okay, you sure? 'Cause I don't mind waiting. Great. Let's look at this. This is what we just talked about. Now I went ahead and put it on here. Let C be a real number that is either an interior point or an endpoint or an interval in the domain of F. The function F is continuous at C if f of x equals f of c. Remember, it has to exist at the point. The function is right continuous at C. Continuous from right. If that also exists. If the limit as x approaches C from the right, this one's the limit as x approaches C. This is the limit as x approaches C from the left. It's left continuous. So when they're both continuous, left and right, that means it's continuous on the entire function. Theorem 6 told us immediately that the function f is continuous on an interval point C of an interval in its domain if and only if both right and continuous at left, right and left. So there is a distinction. It's continuous if and only if both right continuous and left continuous. So it's continuous here because it goes to the right and from the right and from the left. But this one is only continuous from the right. This one's only continuous from the left. We say that a function is continuous over a closed interval if it is right continuous at A, left continuous at B, and continuous on all internal points, where all C inside AB. So in other words, if we have a closed interval, then we have to make sure that the endpoints at least approach those endpoints. If a function is not continuous at C in its domain, we say that f is discontinuous at C and that S has a discontinuity at C. So what does that mean? It's not continuous at C. That means there's a discontinuity, whether it's a jump discontinuity, whether it's a removable discontinuity, it's whatever. It's just not continuous at that point. A function can be continuous, right and left continuous only at a point C that is defined. What does that mean?
Means that when x equals c, then there is L.
Right.
F of c. Right.
Right. So as a function x approaches C, f of c equals L. From both right and left. And the whole thing. So that is itself, it's pretty important. All right, so let's look at another example here. What can you tell me about this function? Are there any discontinuities? Are there?
There would be a discontinuity at x equals 2. Or, I'm sorry, no.
Well, whenever you can, let's graph it. First off, what's our domain? Remember, we have to look at our domain. And what's the graph going to look like? What is the smallest number x can be? Well, let's see. the smallest number you can have inside an absolute value, a radical, is 0. So if we set those equal to 0, we got x equals plus or minus 2.
Well, so 2 is the biggest.
2 is the biggest. 2, yeah. So this is our domain. So we're on a closed interval through 2. Our range, since we're only, you can go from 0, when x is 0, it's 2. We know this is a semicircle. So what about continuity?
Right.
So we have to do the limit as x approaches -2 from the right of our function, which equals 0.
When the limit is x approaches 2 from the left.
It also equals 0. And now every point in between there, what happens?
It's positive.
Well, the limit exists at every point between there. So for every point between -2 and 2, it exists. And since those are the intermediary points or interior points, and our endpoints have limits, even though it's bounded, it's a closed interval, so it's continuous. It's continuous only on -2 and 2. It is a closed interval. Now let's look at example 3. Use the step function u of x, graph below. Is right continuous at 0, but neither left or right continuous nor continuous. Prove it. How would you prove that it's neither left continuous or continuous?
Well, if it isn't left continuous, then it can't be. So.
That's true. If it's not continuous on either left or right at any point in there, then it's not continuous.
So if there's a hole there, it jumps.
Well, why is it not left?
Because it's not approaching the value.
Yes, it is.
Or well, you're gonna just.
At -0.9, at -0.5, at -0.1. But at -0.9, what's the answer? What's the value? At -0.5, at -0.1, at 0, it's 1. So as it approaches 0, it does. No, oh, it's bleeding. Yeah, no, it's too dry.
Yeah.
So does the limit go to 0? No, the limit can't go to 0 because it's open, so it goes to 1. So it's not left continuous. How about right hand side? Yeah, all of these 0.9, 0.7, 0.2, 0.1, they all equal 1. And that's exactly, so it is right continuous. it's not left continuous because the limit as x approaches 0 of our function does not equal 0. All of these values say it's supposed to go to 0, but it jumps to 1. Because it's a jump to continuity, yes. But that's the reason why it's not left continuous. His nose is bleeding. Okay, so now we're going to define the continuity test itself. Right. At here, there is a jump discontinuity. When x equals 0. Okay. Now we can define continuity. We've been talking about it. Let's define it. What's this? At an interior point or an endpoint of an interval in its domain, a function is continuous at points where it passes the following test. F of c has to exist. F of x has to exist as x approaches c. And then they have to be the same. So the limit as x approaches c of f of x has to equal L. The limit as x approaches c of f of x equals f of x, or f of c, and f of c has to equal L. That'd be the same. Now, what this means is we have to be able to go from left and we have to go from right.
I think it's what it says on the last page, couple of pages, we saw that on that, that's good to, from the right continuous scale. I think there was, I think,
Let's see. This one here?
yeah.
Yes, because it has to be continuous from the right, has to be continuous from the left. So that's then, if that's true, because they're going to the same values, they're all going to f of c, and this equals L. So all of these have to go to the same value.
So that's how we check if it's continuous as well.
Right. We have to check 3 things. We have to first plug in the number inside the function, see if it exists, and then check both sides if they're approaching the same number. See, the problem with that is the limit of this function as x approaches c, it exists and it's 5. But does f of c actually exist? No, does not exist. It's no, yeah, it's, or if it's a removal of discontinuity. And let's say that equals 7. They're not equal, so it's not continuous. So that's why it can't be a jump discontinuity. It can't be a removal discontinuity, and there are other couple other conditions we'll get to. Yeah, so these are the big ones that we have to look at. Look at this example. The function of y equals greatest integer value of x is graphed below. It's y equals, this is the notation for it. Okay,
Yeah, I decided to like put a towel in it.
and stop. Good. Want to see the rest of the stuff? We just went ahead and defined the continuity test.
Oh, I already looked at the continuity.
Okay.
So I think I'm good. Up to
Perfect.
this point, like this is where I stopped.
Okay, so let's look at the greatest integer function. Prove that it's continuous or not continuous. How would you do it? Is it continuous? And why? That's the important part. It's always the why that's important.
You know, if we don't answer the why, then we'll very quickly just AI.
Yeah. All you answer, no. Because the whole pencil thing, if you lift up your pencil, it's not continuous. But why isn't it? Remember, to prove continuity, what are our 3 conditions? And basically it tells us that the limit as f of x as x approaches c has a limit and it's L. So that tells us that f of c has to equal L. Yeah. Well, let's see. Let's look at any of the integer points. Let's try one if we see that one better. At x equals 1. When x equals 1. Does f of 1 exist? It equals 1. Does the limit of f of x as x approaches 1, does that exist? No. Why doesn't it? Because in order to exist, it has to approach from both sides. From the left-hand side, where does it approach? 0. From the right-hand side, it approaches 1. So that's the reason why, because limit as x approaches 1 from the left equals 0. The limit as x approaches 1 from the right equals 1, and they're not equal. Because yeah, that should also go in there somewhere. The limit as x approaches c from the left equals f of c. The limit as x approaches c from the right has to exist, and they have to be equal.
You're including the parts from the one-sided function.
You have to, but yeah, because I know I'm jumping ahead, but in order to be continuous, as we said from last section, that if you have a point, a limit at a point, it has to have both directions. So let's go ahead and jump it in there. The book's gonna talk about it later on, but I think this is a perfect place to talk about it because right here, I mean,
Yeah, it's happening.
it's happening. Yeah, it's exactly what's happening. So the limits from both sides have to approach the same value and they have to be equal. And these have to equal this one, which has to equal the limit. All of those have to be true. And if it's not, if any one of those fail, then it's just not continuous for whatever reason. Yeah, you see, now you see why when I first asked you guys, define continuity. And you said, well, you can't lift the pen. There's a lot more to it than lifting your pen. It's all these other numbers you have to figure out.
And that, we're trying to figure out how can we make it as precise as possible, is that right?
Yes, because you can't have any unanswered questions. That's come on any proof, any theorem. You have to look at every possible combination. A theorem cannot exist until all tests have been given. If there's one condition where it doesn't, then it fails.
All fixed it just for-
Right. It's called a counterpositive. Once you find one of them that proves it wrong, say like Pythagorean theorem. If we can find two sets of numbers when you square them doesn't equal c squared, it throws the whole thing. We can't use it anymore.
We would just be, you know, what,
Bye. Adios, Pythagoras.
2,000 years ago.
So yeah, everything we've designed since then was wrong. I hear see. I hear.
Throw our laptops out.
Here are some common ways for a function to fail continuity. So what do you think some of the possibilities of failing? What do you think some examples of failing continuity would be?
Well, the woman don't.
Yeah. Well, we talked about that, yeah. Jump. No better.
Removable dysfunction.
Yeah, yeah, give that one. Removable. What else?
If it's an endpoint.
Yes. We'll go, yeah. Why?
Because it can't be continuous.
You can't check on both sides, yes. Can't check it from the left. Anything else? Jump discontinuity, remove discontinuity, and endpoint. Those are pretty much the big ones. How about oscillating functions?
Yeah. Oscillates between -1
Like sine and cosine, right? It oscillates between one and -1. So we look at oscillating. even though it is continuous, our values change from -1 to +1. It all depends on how the frequency, how fast it changes there. Let me see, do I want that one yet? Why not? Let's just do that. Let's look at this one. The function f of x equals 1 over x is graphed below. Is a continuous function. It is continuous at every point on its domain. Is it? True or false? Just think about the definition of continuity.
Well, I guess,
Well, because here's the kicker. Every point on its domain. What is its domain? If the domain is -infinity to +infinity, no.
right, 0.
Because yeah, what happens at 0? On the left-hand side, it's going to -infinity. On the right-hand side, it's going to +infinity. So that's a discontinuity. But what if I just take one of these two? Then it's continuous on the left-hand side, only on the left-hand side, and continuous on the right-hand side. Except at the endpoint. Because there is no endpoint, because we can never get to +infinity.
Right. So it's discontinuous unless you partition the domain.
Well, yeah, if we do this, then but even at that, since we can't define the endpoint, is it continuous?
Well, it's continuous over an open interval, right?
To an open interval, yeah, but now if we're looking at closed intervals also. What we call this, since it goes on to infinity, we call that an infinite discontinuity. Because it goes to infinity. Well, if I go this way, it goes to infinity, -infinity, now it's +infinity. Or if I looked at the function 1 over x squared, what's that graph look like? Now we're both going to +infinity. That's an infinite discontinuity. But since these are going in different directions, there is discontinuous. Not even a jump discontinuity because it doesn't continue. Because we can't go to 0.
And the second one, the x squared is infinite.
Right. We get infinitely close to 0, our limit goes to infinity. So as our limit, as x goes to 0 of our function, it goes to infinity. Is it the same on both sides? That's what you have to check. As x goes to 0 from the left, 1 over x squared equals infinity. The limit as x approaches 0 from the right of 1 over x squared equals infinity. And they're equal. So limit is infinity. It's a discontinuous function, yes, but the limit is infinity.
So it's infinite.
Yeah, because as we get closer to 0, it just disappears. All right, let's see what else we got here. Yeah, we talk about oscillating functions. Oh, here we go. What do we have there? Well, properties. Let's do properties first. I was gonna give you, I had this example sheet I'm gonna show you, but not yet. Theorem 8. Properties of continuous functions. Oh my, handwriting's horrible. This is similar to the algebra of functions. Remember what that means, the algebra of functions? The first one,
Oh, we're talking about like, okay, yeah, like doing
That's what-
operations.
right. So we have our first one is that f plus g. Well, first off, let's define f and g are continuous functions with a limit of x or f as x approaches c is equal to L. The limit of g as x approaches c is equal to m.
When you say, yeah, like the one that's X approaches CFF. Plus the one that is X approaches CFG equals.
Right. So
L.
So the limit, the sum limit says that I can break these up. Equals L plus M. You can either combine the two functions together and then take the limit, or you can separate the two functions and take the limit separately and add the solutions. The difference. The limit of f minus g as x approaches c. This is the same as the limit as x approaches c of f minus the limit as x approaches c of g, which is equal to L minus g, or L minus m. Yeah. The constant multiple. What does that mean?
You multiply it by some.
So if you have a constant multiple in your function, you can factor it out. You can factor out the constant number out of the entire limit. So that equals k times the limit. The product property. The limit of f times g as x approaches c. You know, these are supposed to have of x in there. I'm leaving off the of x. They're functions of x. So I split them up as the separate limits of each other. So that becomes L times M. The quotient property. The limit as x approaches c of f over g. Limit as x approaches c of f over the limit as x approaches c of g equals L over M. If g of x does not equal 0. Because it has to be defined since it's the denominator. All right, the next one's going to be exponents, powers. Up 6. This one says the limit of f of x to the power n as x approaches c is equal to the L to the power n. But n has to be positive. Because what happens if it's negative?
Then it would, create
It should be a quotient rule then, and then this would be on the bottom. And then the nth root. Any roots. These two actually go together because of the exponential rule. If n is a rational expression, then you have a root. What really happens is this exponent becomes, and this radical becomes an exponent, which from rule 6, it gives us what puts that in there. So yeah, it just jumps in from there.
So it's basically just it's just another way of writing.
Right.
Yeah.
The exponent. So this is when n is rational. If it's a fraction, do the same thing. Let's look at this. Right? You should. If I'm going too fast, stop me, please, please, please. I really don't mind slowing down. Example 6. Every polynomial p equals a n x to the power n a n minus 1. So is continuous because p of x equals p of c by theorem 2, which just plug it in there and it works. Why? Because there are no possibilities of a discontinuity in there. If p of x and q of x are polynomials, then the rational function p over q is continuous whenever it defines this. So let's look, let me give you an example here. P of x is equal to find the limit of P of X as X goes to 0. Is this a continuous function? Are there any polynomials you could think of that would be discontinuous? No, because all of the x's, the only thing that can make it discontinuous are all in the numerator. And they just have powers. So no matter what your coefficients are, whether they're radicals, whether they're rationals, whether they're integers, doesn't matter. It's just the x that matters. And x's are always x to some power. And we know it's continuous because we get a derivative of it and it's still continuous. So what would this limit be? Yeah. Because all these x's go to 0, so it's just constant. What would the graph look like?
Well, oh, do you count the exponents to get the number of turning?
No, let me see turning points. 1, 2, no, we'll still have 3, because we'll have 3 vertices. Because all this tells us is the number of solutions,
Oh, okay.
which are the x-intercepts.
Yeah.
So this one would look something like this.
So we know that it would have a y-intercept of 4.
At the y-intercept of 4, exactly. And we know we have. So in essence, we only have really 2 turning points. It goes down here, then it. And how do we find those? Take a second derivative set equals 0. The points of inflection.
That's how you find them. You
Yeah.
take the second derivative.
Oh, I'm sorry, this is Cal 1. Yes.
Well, I'm
Yeah.
curious.
Because second derivative finds points of inflection, which are the turning points. It stops from concave up and stops being concave down. Concave up. So it's just think of bowls. So this bowl is always going down until here. Well, think of an airplane or a roller coaster. Well, not a roller coaster. If you're a pilot and you're going down, and all of a sudden you start pulling up. At some point, you have to stop pulling up and start pushing down to start going down again. This is the point where you start pushing down, the point of inflection. That's the point of second derivative. I forgot we haven't got that far yet.
If you were to write the second derivative with this, would you write 10x to the power of 2 minus?
Well, the first derivative would be 20 x to the third. Take the first derivative and then second derivative.
Oh, so you have to take the first and then find the second.
Yeah, well, yeah, I forgot. I gave it with you guys. I forgot we're not that far yet. So, shh. So, yeah, so our limit exists. It's always continuous. It's always continuous because the x's can never be in the denominator. Their coefficient or exponents are always positive. That's why this one's going to be always continuous. Okay, let's look at number 7. Prove to me this, Batman. Why is this continuous? Get my next example ready. There.
Well, it's defined that all numbers in its domain. All x in its domain.
What does the graph look like?
The absolute value one, so it's like that.
It's the V. So at 0 would be the question. What happens when x is less than 0? And then what happens when x is greater than 0?
when X is less than 0, it's, well, the X is negative, but it's still a positive number. So f of X is still a positive number.
Okay, so as in
Well,
this
it
segment,
approaches,
so this is, it's going less than 0. So was it approaching? And then we also have to look at this question.
so if you go from the left, f of X equals 0.
Well, yeah, because it's getting smaller and smaller and smaller, 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 smaller.
And the same goes for the right side.
And we know that our domain, our range cannot be negative. So we know that this one approaches 0. From the right-hand side, it's also approaching 0. And then at f of 0, we got 0. So that's the limit as x equals 0.
By the same.
Yeah, you said by
So it isn't.
it is continuous. Okay. Ooh. Inverse functions.
Add an inverse to something, it always makes it sound scary, right?
Yeah. So how would we look at what are inverse functions?
Switch the domain. So the domain of the regular function becomes the range of the inverse.
Right. So switch X and Y. That's what it tells us to do. So the domain becomes the range, and the range becomes the domain. I think here's an example for this. If f of x is continuous on the interval AB, then its inverse must be continuous. On the interval CD. I think of looking at example one. I think of an example where inverse isn't continuous. Linear equations are continuous. Radical or exponentials are continuous because the inverse of that's the radical. Rationals
But
are.
with the radicals, you can't have a negative number.
Yeah, but it has an endpoint. So
Oh.
in that domain will start at the endpoint. Basically, what it's saying here is this. The domain is the tough part. Those are the x values. Whatever x values exist that are valid for the function, then you have an output. That means the output's already safe to begin with. So if I start off with something that's safe, I automatically know I can go to something that's going to work. See what I'm saying? So, like for the radicals, I know that for radical x, I know that for my radical x, my domain is from 0 to infinity. That's my domain. What's my range? Remember, a radical function looks like this. Yeah, so that means my inverse function will also have the same domain and range. So this is the domain and range. It flops. So it's a lot easier because if it's defined, if it's a continuous function f of x, and you find the inverse of it, then the inverse has to be continuous. All trig functions are continuous. So their inverses are continuous. But think of the inverse of cosine. What is it? 1 over secant. Or secant, 1 over cosine. And what does that graph look like? Or no, secant looks, I'm sorry, if cosine of 1 is 0, so it looks like this. Yeah, so these are my asymptotes. So the secant function looks like this.
Yeah, I was thinking about that for a second, because it has those asymptotes, so it's still continuous.
It's continuous because remember, on our domain, this is A, this is B. So anywhere that the denominator is not equal to 0, that's my new domain.
And it's continuous.
I misspelled there, Their. Yeah, and they're continuous on the interval. So once you define the interval, then it's okay. Logarithmic functions. What's the inverse of a log function?
And exponential.
Or this is
Wouldn't that
whatever,
be exponential?
in this, yeah, because we have 3 of them. We have log n of x, which is, that's the inverse. Log of x is 10 to the x. And ln x is e to the x. These are the inverses. Remember, log base nothing is 10, because it's base 10. Log of ln is log base e, so. Let's see what else do I have here. Nothing for that one. So we looked at inverse functions, we looked at regular functions, trig functions, exponentials, logarithmic. How about composite functions?
Yes. It was awesome.
So what would the new domain be?
The domain of the, trying to think of, like,
I know,
so
once you
like,
know, once
yeah.
you're looking at this,
Like, I know it is continuous, but finding out how to describe it is the problem.
yeah, if f and g are both continuous, then the composite function of f and g has to be continuous. Are you done with this? You done with this? Okay. All right, now let's look at composite functions. And continuity. So a composite function looks like this. So we're going to presume that the limit of f of x as x approaches c is equal to L, and the limit of g of x as x approaches c is m. Because they both have to be continuous functions to begin with. So this is the fog, it's the Fog and Goff thing. Remember that in algebra? So since f of x and g of x are both continuous, so in order, g of x is continuous, right? So if we take the limit as x approaches c of f of the limit of g as x approaches c, what we're actually getting is the function of, so yeah, so we're gonna take this value, put it inside the function f, whatever that equals is gonna be our answer. And it's gonna be continuous, because if it's continuous in G and it's continuous in L, or F, it has to be continuous in the composition of both.
It's easier than it was.
Well, that's why I'm hesitating showing you the picture.
Yeah.
But yeah, the composition is always, as long as F and G are both continuous, the composition is function of this function is continuous as well. Let me show you the picture. I shouldn't present, but this is the picture I always screw up. Here's our value C. F is continuous at C. This is our first function. So we have f of c. That one works. G is continuous at C. So that one works. So this one is G of f. Because the way we would do it for the other one is here's C, G continuous at C, which means that we get from here, we get G of C. And F is continuous at G of C. So that tells us this is F of G of C. So what is this thing telling us actually? Remember, F of G is actually F of G of X. Let's see, of C. This is a continuous function. So we first have to take the limit of the inside. Since it's continuous, it has to exist. So what we get there is that limit. So since G is continuous, and then L is, that means F is, this M has to be in the interval AB for the function A, function F. So since it's an element in there, it's defined, it equals some value L. So the value of G of C inside F is the same value that we get there. That's what we're saying. If f of x is a continuous function at x equals c, and g is continuous at x equals fc, then this is also continuous. And conversely down here, as x approaches c. It sounds straightforward, and it really is. And it's always going to be continuous. So let's look at an example. Exactly. These don't tell us much. Examples tell us a lot more.
Right.
Okay, we have 4 of them. show that the following, okay, notice that, are these composite functions?
Which ones?
All four of them. Let's say f of x equals square root of x. Let's say g of x equals x squared minus 2x minus 5. So f of g of x would equal, yes, and the next one, let's say f of x equals 1 or x over y. Or let's even say x 2/3 over g of x. It is a composite function because g of x would be that bottom number. Same thing here. F of x is the absolute value of x. G of x is that inside there.
And so we actually break them apart, their natural domain. Would that be the original two parts of the function?
Yes, we have to, the domain of the result will be the domain of the least part of the functions. So in other words, if f of x, like this one here, is from 0 to infinity, this one's from negative infinity to infinity, that means the composite function is only continuous on that part. You can only take the domain of your result can only be the smallest domain of your functions. And that's the same thing as it works in the algebra functions. We had the sum, the difference like that. Whenever you do that, it's always the domain of the smallest part. Because what we're looking at here is just they're overlapping. So show the following functions are continuous on their natural domains. Notice they're on their natural domains. What's the domain of the first one?
Sure.
Are you sure?
Well, that would be for the root x, but if you actually consider the g of x in there as well, that would be negative, I mean, it would be 5, right? Or not 5.
Let's see where it equals 0.
If you use a quadrant. Well,
minus 2x. Oh, no.
So yeah, we can't use factoring here because what times what is 5 when you subtract me at 3? We can't do that. So we gotta use the quadratic formula. So, and that would tell us our two possible values that would give us for x. But once we find that, we know the value, the graph of this. Because once we find where the two intercepts are, if it has 2, then we can't use whatever's behind here. So our domain would be from negative infinity to a, and then from b to positive infinity. So that would redefine our domains. Okay, let's go ahead and start. Let's do A. So we have y equals square root of x squared minus 2x minus 5. We have another theorem coming up. So show that the following conditions are continuous on their domain. So we have f of x equals the square root of x, which is from 0 to infinity. We have g of x, which is x squared minus 2x minus 5, which is from negative infinity to positive infinity. So since we have a composite function, we can only use the domain of 0 to positive infinity. On the domain Since this function is continuous on this domain, and this one's from negative infinity to positive infinity, then it has to be continuous on this. But the problem is that we don't know about this one. Even though this is a continuous function, can 0 be used in there? Then we get a -5 and we can't do it. So we have to find the domain of both of these put together. So x equals a is 1, b is -2, c is -5. Negative b plus minus b squared, or ac over 2a. So negative over -2 plus or minus -2 squared, 4 times 1 times -5.
24.
Let's see, it's 2, 4 plus 20, 24. 2 plus or minus radical 24.
So 3.4 and -1.
2 plus 2 radical 6 equals 1 plus radical 6, plus minus radical 6. So what that says is 1 minus radical 6 and 1 plus radical 6. Those are my x-intercepts. So we can't use anything between there. Yeah, because it'll give us a negative answer. So our domain really is negative infinity to 1 minus radical 6, 1 plus radical 6 to infinity. So, but this one has to be positive. So that's our domain.
So anything that's inside of that parabola, it's gonna give you a
Negative answer, which means we can't take a radical of it. It'll give us imaginary. Let's look at B.
And so that's your domain, right?
That's my domain. Yeah, it's continuous. We know it's continuous there because we know that both of these are continuous individually. But since this one's restricted, we can only take the upper half. So we have F over G. Let's look at that. Is the top number restricted? No, because it can be positive, it can be negative, it can be 0. And since it's a cube root, it can be positive, negative, or 0. How about the bottom? Can the bottom ever be 0?
It's just give that +1.
Can anything to an even power be negative?
No.
No. So it's going to be 1 plus a positive number. So we have here from negative infinity to positive infinity. So it's continuous everywhere. Letter C. That one I. Y equals absolute value of x minus 2, x squared minus 2. And this is for next time. X sine X, X squared plus 2. So we're going to do C. What's my restriction? We have a fraction, right? So the only thing we cannot have on the bottom is it cannot equal 0.
Okay, so
So X cannot equal plus or minus radical 2. It's continuous everywhere except there. And we don't have a removable continuity, so we're stuck. How about the last one? Does the top have any restrictions?
No.
No, because sine is bounded by 1, -1, infinity, negative infinity. X is infinity, negative infinity. On the bottom, X squared plus 2 can never equal 0. So this one is from negative infinity to positive infinity. All real numbers. Make sense? So we just have to look at the whole function itself. If you have a rational number, is there any X that'll make the top undefined? No. There's X in sine, it could be anything. So that one's unlimited. On the bottom is the only thing, it can't be 0. So if nothing contradicts that, we're okay for everything. So that one's continuous everywhere throughout the entire thing. All right. Limits of continuous functions. Limits of continuous functions. If f of x equals b, if the limit of f of x as x approaches c equals b, and g is continuous at point b, then the limit as x approaches c of this is that. Well, this is what we just said of the composite functions. Because this right here is the g of f. If we take the limit, of the inside, remember the way I did it was I used the L and M. So the limit of f of x is that. That's the input for the g of x. So it's the limit of g of this function. Let's look at this. Hold it. Let's say the limit as x approaches 2 of 2x. That equals what? 4. So the limit as x approaches 2 of 3 times 2x I'm doing this. That's what this is all about. So the first thing I do is I know the limit of 2 of as x of x approaches 2 is 4. And that equals 12, and that's the limit of it. That's all there is to it. Let's look at examples here. Applications of theorem 10. cosine of 2x plus sine 3 pi over 2 plus x. So for the first one we'll do is x approaches pi over 2. Let's look at that one. Do that one first. So we have to first take the limit of the inside. Because this is g of f of x. So we have to first take the limit of the inside. So the limit as x approaches pi over 2 of 2x plus the limit as x approaches pi over 2 of sine 3 pi over 2 plus x. And the cosine out in front, because we're gonna take the limit outside. So the limit as x approaches pi over 2, this one becomes pi. When x is pi over 2, 2's cancel. Pi over 3 pi over 2 plus pi over 2 equals 4 pi over 2 is 2 pi. And the sine of 2 pi is
Or, I mean,
0.
pi plus 0 equals cosine pi.
Yeah, but cosine of 0 also equals, no, this equals -1, this equals 1. But we're looking at pi over 2. Yeah, but there aren't any more x's in there. So we have the cosine of pi plus the cosine of, or we're gonna get it this way, 0 plus pi is negative. Yeah, I'm thinking, well, no, we could do we can't do the inside. We have to, right, exactly. So yeah, all we do is just plug in our value for x inside there and go for it. It looks more complicated than it is because of all the pi over 3s, 3 pi over 4s.
It's always like that. That's one of the things that I like that.
It makes much easier than it is. Question. This part? Because 3 pi over 2 plus pi over 2 is 4 pi, is 2 pi. Sine of 2 pi is 0. I know. Again, all the writing parts are more difficult because you get confused. And so pi plus 0 is pi, so cosine of pi is -1. What's the next one? We have sine of -1 of 1 minus x over 1 minus x squared. What's the limit of this one? This one's going to be as x approaches 1. Because that's the only part that would make it mess up. And what this one's going to do is x approaches 0 on the last one. I'm sorry, that's because if 1 would give us a problem. So that's why we're going to do 1. But what do we do first? If we plug in, so if we're looking at limit of as x approaches 1 of the inverse of sine of 1 minus x over 1 minus x squared. If we plug in 1 inside here, what do we get? 0 over 0. Whenever you have 0 over 0, what can happen? Right. Inverse of sine, so we have 1 minus x And this one is 1 minus x, 1 plus x. It's the difference of two squares on the bottom. Mhm. So if we plug that in there, what do we get?
I. Or I'm sorry, it's pi
No.
over 6.
Pi over 6, yeah. Pi over 2.
Yeah, pi over 2. That's always what gets me easy. Thing radians. It's like you go through all of grade school learning.
Yeah, exactly. You do the
It's the same
radians
thing
in
with
there. Oh, yeah. That's growing up around the world. Yeah, it's so yeah, so that's your answer. And the third one is the radical x plus 1 times e tangent x, not tangent x. This is tangent x. Ever get that written down? That's the one we're going to do right now. Oops, let me write that down. So
E to the power of tangent x.
yeah, radical x plus 1 e tangent x. This is as x approaches 0. What do you do first?
Well, if you plug in 0 for x,
That's good.
tangent 0 is undefined. Or it's not undefined, it's just 0. So we've got e to the power of 0 equals 1. Root 1, 1 plus 1, or 1 times 1.
So this is sine of 0 over cosine of 0, which is 0 over 1, which is 0. So radical 1 e to the power 0, 1 times 1 equals 1. Pretty good. It looked ugly, It looks ugly. but then once you said, that's pretty easy. Okay, we're out of time for today, so we'll finish up the chapter next time. What do you think?
I mean,
I feel pretty good about it. I think I really do